thank you for coming to the Israeli Day. Unfortunately, last year we couldn't have the event for obvious reasons, but we're very happy to have the event this year. So we'll have two long talks to start the morning. Asaf will give the first talk, and then Niva will give another long talk, and then we'll have a sequence of 8 short talks by students. And then we'll have a postal session over lunch at 12:30, and then after lunch we'll have Sigal give a talk. Unfortunately, Shiri didn't feel well, so I'll give the talk instead of her afterwards, and then Yoav will give the talk, and Yaakov will give the last talk. So we're happy to have Asaf Rom here from the Rationality Center here in the university, and the Department of Economics.
Pending, right?
What?
Pending?
Pending Rationality, okay. I didn't, and he's going to talk about partial two-sided matching.
Good. Hi. Partial two-sided matching. So this is joint work with Avinatan Hasidim from Google and I think still in Bar Ilan, and Ran Shoer from Penn State. And the motivation is that we try to אפשר להנמיך אותי טיפה?
תוריד את זה טיפה.
לא, אבל, אוקיי. לא יהיה יותר קל. אפשר פשוט שזה לא יוגבר, כן?
אסף, זה אולי
אפשר כבר שעשיתי שבלתי. בסדר, שליש אותי. אני הולך להפסיק עם זה, להשתמש בזה. בסדר?
השאלה אם זה מחובר להקלטה.
זה גם מחובר להקלטה. אבל עכשיו אני בחוד.
זה התחיל מההתחלה עם ההצגה של...
לא, זה בסדר. סליחה, אני... תודה, סליחה. So it's when we're doing matching, it's only interesting when we're talking about situations where people can deviate later from the matching. If they cannot deviate, we can just decide on the matching and that it would be implemented. That's why usually when we talk about market design, we talk about stable matchings. Matchings that if we recommend them, they are likely to stick. People would adhere to them because they cannot deviate with other agents. However, when we have partial participation, so some of the agents in our market participate in a centralized matching system and the others don't, it doesn't make a lot of sense to talk about stability, okay, because people might deviate ex post with people who did not participate in the centralized matching system, okay, so we can maybe output a stable match with respect to those agents that do participate, but it would not be stable with respect to the whole market, okay? And that is why nobody ever does that. Nobody ever designs a matching mechanism unless you have full participation of everyone, okay? And not only do people not do it in practice, there is also no acceptable, no reasonable, no theory at all that deals with this situation, okay? However, sometimes, I'm sorry I'm not at the order of the bullet points here, but sometimes a market design is needed, okay? Sometimes markets do need a redesign because there is severe unraveling, or because there are exploding offers, or because there are all sorts of market maladies, okay, that happen, and despite that we don't have full participation, so we want to do something despite the fact that we don't have all the agents, okay? And this is exactly what happened in the low internship match in Israel, let me tell you just a bit about that, but not a lot. So up until 2012, to get a low internship, you would usually get an offer around your end of first year of undergrad or beginning of the second year of undergrad to get a low internship for after you finish your 3.5 years of law, okay? And that was really problematic because people didn't know what kind of internship they want, and the firms didn't have any information about the students except for their maybe bagrut grades, okay? And first semester of law school. And then in 2013, the Bar Association and the Ministry of Law decided that Ministry of Justice? Okay, Justice. Decided that they are going to set a specific date before which you cannot offer a position, an internship position. Okay, so what happened is that the competition that before that manifested as unraveling transformed into a competition that looks like exploding offers, and suddenly everybody gave an offer exactly at the right time when people could get an offer, and there were very stressful offers because you'd get a phone call and you'd not know whether you should say yes or no, and if you said no, that offer is off the table. Okay. And the Bar Association and the Ministry of Justice were not very eager to try to use a centralized matching system. How do I know? Because I offered it twice. I went to them and I offered it for free, and they didn't want it. Of course, maybe suggesting it for free maybe was not a good strategy here, but they didn't want it. So in 2017, I was approached by the Hebrew University Law School to try to help our own students, okay, the Hebrew University students, in knowing which exploding offers they should say yes or no to, okay? And what we decided to do is to create some kind of a matching recommendation system, so a recommendation system based on a matching system, okay? But it only gives recommendation, it doesn't actually match people, and it's voluntary participation, so students could decide whether or not to participate, okay? So actually first year, it was only Hebrew University students, and they kind of had to participate, okay? Second, because it was initiated by the vice dean of students in the Hebrew University, so it kind of made them do it. But then years after, we opened it to any student who wanted to do it, but not everybody participated. And as for firms, we started with the big firms that usually hire students from the Hebrew University, but then we opened it to all the firms, but still not everybody joined, okay? So we hope to start small and eventually somehow reach full participation that will allow us to build a matching system, and that's actually what happened, okay? So we had this system for 3 years. Let me just search. 3 years. The first year we only had Hebrew University students. That's like 10% of the market maybe. And eventually we had almost everyone. Not exactly everyone, but almost everyone. And as we went forward, we got, what we were able to do is to give better and better recommendations, okay? Now, the one thing that we decided in advance is that because we're doing a partial matching design, partial market design, we would not give recommendations that wouldn't stick. We only want to give recommendations that eventually would be implemented, okay? Meaning that we decided intentionally not to match everyone. Some people who could have been matched, some interns that could have been matched with firms, we decided not to match them because we thought there might be a good possibility that they would actually eventually match with someone who is not in our system, okay? How did we know that? So that was a feature that we didn't thought about it initially, but it ended up being important. We actually asked the participants, both interns and firms, to provide us with their preferences over all the participants, all the possible matches, including those not in our system. So for example, for firms, we asked them to rank participants not by their names that they could choose in the system, but by their ID number. And they always knew the ID number of those people that they interviewed, so they could just give us their full preferences over everyone, whether they're in the Hebrew University or not, okay? And similar for the students, because we didn't know which firms are going to participate eventually, we just created the full list of firms that hire interns and asked them to choose from that, okay? And later, some of them participate, some of those firms participate and some didn't. So we didn't match all the participants, okay? But those that we did match, we later checked whether or not they actually got a recommendation, okay? We thought that even if,
So each student ranks all the firms, each firm ranks all the students.
Right, but eventually you only have some of them.
You only have Hebrew University.
Right. First year we only had Hebrew University, but then after that we had also Bar Ilan and Haifa, I think, and Sapir, and then last year we had almost everyone.
Okay. So
And then 2020 until 2022, I think, it was an actual matching system. It was still a recommendation system, but we had all the participants.
okay, so you have full rankings of every agent. So and then you do what algorithm?
Yeah, that's the top.
Okay. So you answer algorithm, and then you have a So you have the algorithm finds a partial matching, not a complete matching.
Correct.
Okay.
Yeah, that's why I call it partial matching. So this talking about the theory that underlies the system, although when we did it, we didn't have the theory. Okay? I just came up with it like a year or two ago, but we basically use the same sort of algorithm that I'm going to present today. Okay, so I'm going to introduce a new concept called safe matching, which is a replacement for stable matching. Okay, and the idea of safe matching is going to be, I'm going to give you already the point. The idea of safe matching is going to be, I'm going to give a recommendation that would stick. Okay, I want to give something that people could not deviate from. It's not imperative that I would match anyone that they could match, everyone that they could match, but those that they do match, I want them to adhere to the recommendation. Okay, and it's easy. It's easy to find a safe matching, right? Because I can always say my recommendation is nobody does anything. Okay, I don't have a recommendation. That's easy to find a safe matching. But the point is to give a maximal safe matching, something that would match the most people I can. Okay, and still would stick. And I'm going to characterize the set of safe. So I'm going to find an algorithm that finds one such maximal safe matching. In fact, it's going to be a side optimal safe matching. Okay, and then I'm going to characterize the entire set of safe matching, maximal and non-maximal. Okay, so here's an example for standard two-sided matching. We have 3 men and 3 women. Okay, and preferences are listed from top to the bottom. So Ross prefers Rachel to Phoebe, and does not like Monica. Does not want to match with Monica at all, obvious reasons. Okay, and similar for the girls. You understand what's going on here. This is one sort of matching. Okay, this matching is stable. You cannot deviate from it because all the men get their first pick, right? So the women may want to deviate, but they cannot deviate because no man wants to deviate. Okay. Here is another matching. This is also stable. Okay, and here the women get their first pick. So again, nobody wants to deviate. That's standard two-sided matching. Okay. Here is partial two-sided matching. The difference here is I added Richard. Richard is someone that Monica likes more than Chandler, but is not in my system. Okay. So now, what can I do? What kind of matchings can I think about and maybe output? So this is one possible matching, the matching that I had before, the red one. This matching is definitely problematic. Sorry, it might be problematic, okay, because I don't know if Richard likes Monica or not. He's not in my system, right? I know he exists, I know Monica prefers him to Chandler. If I publish this matching, if I recommend this matching, I might end up with Monica not being matched with Chandler, okay? And that's not good. I want to only recommend matchings that would be implemented. So my second option, I'm removing Chandler and Monica from the matching. Okay, here is my second suggestion for matching. This matching is also problematic. Why is it problematic? Because Monica, I don't know if she would be with Richard or not. If she would match with Richard, then Chandler would be a free agent, right? And he would like to match with Rachel, and Rachel would like to match with him. Okay? So that's again a blocking pair. Chandler and Rachel are a blocking pair. Okay? But this matching here, this matching does not have this problem. Okay? I do not match Chandler and Monica, but also Chandler cannot block the matching with Rachel because Rachel already gets someone she prefers to Chandler. Okay? So that's the gist of what a safe matching is. Here is formal definition. That's the classic definition in stable matching. A market is men, women, finite sets, everything is simple. Okay? Men, women, and preferences. Preferences are such that a man prefers some of the women, okay? I can rank them one after another, and then he also has to rank himself, meaning staying single. So, like Ross liked Rachel and then Phoebe, and then himself, and then Monica, okay? And same for the women, and the matching is a function from men and women to men and women, such that each man is matched either with a woman, or stays single. Each woman matched with a man or stays single. And if a man is matched with a woman, then this woman is also matched with the man. Okay, that's formal definition. A matching is individually rational if every agent gets at least what he or she gets by staying single. Okay? A matching is blocked by a pair, a man and a woman, if the man prefers the woman to his current match, and the woman prefers this man to her current match. Okay, so that's a blocking pair. And the matching is stable if it's individually rational and not blocked by any pair. Standard definitions. Deferred acceptance, I would assume that most of you have seen deferred acceptance once before, but quickly, an algorithm by Galen and Shapley that says basically every man proposes to his top woman, okay? Then if some woman gets more than one proposal, she rejects some of them, okay? Those that she doesn't like, she keeps one of them, but does not accept the man, she only temporarily holds that man, and then the man that got rejected proposes to the second woman, okay? And again, she chooses from those proposals and keeps one, and again and again and again until we're done, until the algorithm converges and turns, and then we're done and the acceptances become final. Okay, so that's why it's called deferred acceptance. Okay, I'm not accepting immediately, I'm accepting at the end. Here is an example. Ross, Joey, and Chandler proposed to their first option. Okay, that's a different perspective from before. Now both of them proposed to Rachel, so Rachel has to choose between Chandler and Ross. She picks Chandler. Ross now moves to his second option, which is Phoebe, and Phoebe chooses Ross over Joy. Joy turns to Rachel. Rachel picks Joey over Chandler, and Chandler goes to Monica, and we're done. Okay, so that's how we get the result of the deferred acceptance, and the deferred acceptance always outputs a stable matching, and it takes O of n squared operation. Okay, HT. In economics, okay, I might not put that. And it finds the non-optimal stable matching, meaning that out of all the stable matchings possible, we get the one stable matching that all men weakly prefer to all others. Okay? Good. Now partial matching. This is new. I define the support of a matching as the set of agents that are actually matched, do not stay single. Okay? An S matching, poor choice of letters. Okay? An S matching is any matching such that the support is included in S. Why do I need this definition? Think about the whole market as the men and the women, but I only control part of the market, S, and I can only match people who are in this sub-market. Okay? So S for sub. Here is an example. 2 men, 2 women, okay? But I only control men 1 and woman 1. Here it's Ross and Rachel. Okay, Ross and Rachel I control, but I know that Joe and Phoebe are also in the market. Okay? So there are only 2 possible S matchings. Either I match Ross with Rachel or I don't. Okay? So there is the empty matching and there is the one where I match Ross with Rachel. Neither of them is stable. This one is not stable because Ross and Rachel can deviate and be together, right? They are blocking pair. This one is not stable because Rachel and Joey can deviate, okay? Because Rachel likes Joey more than she likes Ross. So that's why it's not stable. Safe matching. A matching is safe if it's individually rational, and every blocking pair is only made of agents that are not matched. Otherwise put, agents that are assigned are never part of a blocking pair, okay? So there are no deviations after the fact. A stable matching is also safe, right? Because if there are no blocking pairs, then also there are no blocking pairs that nobody is matched. But a safe, and also a safe matching always is, which is the empty matching. As I said, I can always recommend nothing, okay? First example, we have 3 men, 2 women, sorry. Men 3, which is Chandler, is not part of my market. Okay, I don't see, he's part of the market, I don't see it in my sub-market, in my centralized system. So because Chandler is not here, I cannot match Rachel, okay, because if I will match Rachel, she will be part of a blocking pair with Chandler, right? So Rachel, I cannot match. Now the fact that I cannot match Rachel means that I can also that I can never also match Ross, okay? So Ross is also never matched in a safe matching, meaning that Phoebe is also not matching the safe matching, meaning that Joey is never matching safe matching, meaning that the only safe matching is the empty matching, in this case. Okay, so this is a case where one single agent not in my market kind of burns the entire market. Here is another example. Here I changed Chandler from the first position to the second position. Okay, so now the fact that Chandler is not in my market doesn't mean that Rachel cannot be matched. It just means that she cannot be matched with Ross, right? So the fact that Chandler is not here rules out those matches, but I can still match Rachel with Joey, Phoebe with Ross, and that would be safe matching. okay? And also there is the empty matching. Fourth option, third example, I have 4 men, 3 women. This is actually the example I started with, okay? And here, Richard is not in the market, meaning that I must burn Monica as well. She cannot be matched in a safe matching, meaning that Chandler cannot be matched in a safe matching, meaning that Rachel cannot be matched with Ross, but can be matched with Joey, and that's my safe matching, and also the empty matching, okay? Okay. When I did this, I kind of assumed that Richard might match with Monica, right? I just want to note here that this is a conservative assumption. I have an agent not in my market. The worst thing that could happen to me as a market designer is that all agents not in my market are going to stay single and be interested in all agents in my market, okay? So you can kind of think of the conservative case, which is what I'm going to go on from now on, as everybody outside the market just have full list of preferences, okay? Full rank order lists. But if you know something about the market that you can put in, like I know that the Supreme Court would never hire an intern from Superior College, okay? For example. So you can rule this option out and do the entire exercise without those options, okay? So I'm doing something which is conservative. Here are my goals. First, prove that there are safe matching with maximal support, meaning that if someone is matched in any safe matching, then there is a safe matching where everybody who is matched in any safe matching is also matched. Okay, so maximal in that strong sense, and find one such matching, and understand the structure of the matching. Okay, so yes.
So don't we potentially have a problem with truthful reporting of preferences? If
Yes, I do. And I will mention it in one slide at the end because it's not. I'm allowing myself some slack here because Galen Shapley was 62 and incentives were 82. So in 20 years, I promise you a fuller answer. But no, but I will say something. Okay. Okay. So to show that there is a maximal matching, okay, that there is a safe matching with maximal support, what I do is I define something called the join of 2 matchings, meaning that give me any 2 matchings and let every man point to the matching, to the partner that he likes better than in those 2 matchings, okay? And that will define a new matching, maybe, called the join, okay? Now why I say maybe, because just this pointing thing doesn't necessarily mean it's a matching, because possibly 2 men would point to the same woman, right? Maybe. So the lemma says, if both mu1 and mu2 are safe, then the new thing I got, the join, is a safe matching. So to prove that, I need to prove that first that it's a matching. Wait, do I have it here? No. First that it's a matching, then that it is safe. Now, in the process of doing that, I also kind of prove that the support of the join is the joint support, is the union of those 2 supports. Okay? Yes.
Support in terms of the men or also in terms of the women?
Support.
Like you.
Support is for both of them. So exactly.
Also
So
all women who are matched.
yeah. So it's easy to show. It's easy to see that if a man is matched in one of them and it's safe, meaning individually rational, then it would also be, then the man would also be matched in the join. Turns out it's also true for the women. But for that I need the safe properties. Okay, the safe. So I showed that, and then a corollary is, I'm not going to do proofs today. Sorry, I don't have time for that. Corollary is there exists a man optimal safe matching. That's easy because give me any 2 safe matchings, I can find one which all the men weakly prefer. Will note it, but and this matching is also maximal, and this thing comes from what Uri asked about, that the support is also the union, okay, for the women as well. So I keep doing unions and unions, and I get to some matching which is a maximal and has and is men optimal and has maximal support. Now, in economics, that would be enough, right? Because I just proved the existence, and that's fine. But we want an algorithm as well, okay? So here's my algorithm. It's called iterated burning deferred acceptance. It's called iterated burning because it's kind of similar to what we saw in the presentation before, that as we move on, as we go through the algorithm, I kind of understand who are the people who would never be matched in a safe matching. Okay? The idea is, let's start with a set of burned agents, which are those people who can never participate in the matching. Those are the people who are just not in my market. Okay? I know they exist because they appear in my preference in the rank order lists, but I cannot control them. So this is the set of burned agents. Then, every round I'm going to run delta B, which is some sort of variant of deferred acceptance. Okay? And this variant is a variant that is exactly designed so that to understand who is going to get burned. Okay? The idea is that men who propose to a burned woman kind of stick with that woman. So burned women have infinite capacity. They catch all the men that propose to them. And men who are burned do not propose to women who are burned, so they can go and burn other women. Okay? But other than that, the market kind of progresses as usual. Okay? Meaning that the same competition between men appears. Okay? And the idea is that we're going to run this variant, see if some agents create a problem. Okay? If so, we're going to burn them, we're going to add them to B, and we're going to start over. Okay? What does it mean to create a problem? So for a man to create a problem means to just propose to a burned woman. Because if a man proposes to a burned woman, he's always going to propose to a burned woman. In any iteration, even if I burn more women and more men, he's always going to propose to a burned woman. This is not true for a woman. A woman creates a problem not if a burned man proposes to her, okay? Because I could, as a woman, now I identify as a woman, okay? I can get a proposal from a burned man, okay? And then after that, I would get a proposal from another man who's not burned, that I would reject that man. So maybe that man caused even a chain of events that got me another proposal, but eventually I would get someone who I rank above this other man, so that's fine. I don't need to worry about deviations with that burned man, okay? So a woman is only problematic if at the end of the round she's matched with the burned man, okay? So the algorithm now is run the deferred acceptance thing. If any men are matched to a burned woman, immediately burn them and reiterate. If no men are matched to a burned woman, then, but there is a woman matched to a burned man, burn her and reiterate, okay? And then maybe more men would be burned. And if nobody is burned, then we're done, okay? Turns out that this structure, this simple structure, is really important. Do it any other way, it wouldn't work, okay? Why wouldn't it work? So the theorem is that this iterated Bergen deferred acceptance outputs the man optimal safe matching. What do I need to do to prove that it outputs a safe matching? It's clear that it outputs a safe matching. Why? Because I keep burning people until I get to a safe matching. Eventually there will be the empty matching. So at some point I will get to a safe matching. The question is whether I'm not burning too many people. I need to burn exactly the correct set of people. And to do that, I'm kind of, I need to show that if I'm burning a man, then this man would be burned in any possible safe matching that might, that does not include the set B, okay? And that means that I can burn him right away. And for the woman, something similar that says, if this woman is burned right now in this step in the algorithm, then she would eventually be burned. Now, turns out that a woman can be burned in one round, but then not burned in another round, not burned, but eventually she will be burned again. So that's the difficult part, okay, to show that eventually she will be burned. Okay, now I want to understand how shall I have it alone?
30 minutes.
Good. I want to understand how does the set of safe matching look like, okay, so first, intuition, okay? Suppose I had a market which is hierarchical, meaning that everybody agrees on the ranking of men and everybody agrees on the ranking of women, okay? What is the set of safe matching here? So I could have the empty matching, okay, which is safe. I could also match Ross with Rachel, but that's it, and it will be fine because nobody would want to deviate. I can match Ross with Rachel, Joe with Phoebe, and that's it. Or I can match all three pairs, right, and that would be fine. I cannot match Joe with Phoebe and that's it, although they're in the same kind of tier, right? They're both second in the order, because if I do that, then Ross might deviate with Phoebe, right? Because I don't really know Ross's preferences, okay? So that's the intuition for hierarchical markets. Another market for which I kind of understand the structure of safe matching is separate markets. So suppose I have 4 men, 4 women, okay? But really, if I look closely, I see that those 2 men are only interested in those 2 women, and those 2 men are only interested in those 2 women, and vice versa, okay? Not vice versa, the same. Those 2. This is one market, left side market, and right side market, okay? What is the set of safe matchings in these markets? Well, it's just the cross product of the safe matchings for the left market and the safe matchings for the right market, because they just don't interact. That's why when I do a matching system for medical interns, I don't need to also do a matching for law interns at the same time. I can do it separately, right? Okay. Now, one last thing, suppose I have a safe matching. Suppose I already have a safe matching and I know that Joey is matched with Monica in this safe matching. What do I also know? I also know that if Joey is matched with Monica, then Rachel and Phoebe must also be matched. If they're not matched, then there is a blocking pair. And also, Chandler must be matched. Meaning that given a specific safe matching, the structure of the safe matching is a union of heads of rank orders list. I take the prefix of the rank order list and I just do a union. It must be that, okay? Which kind of reminds me of both the hierarchical thing and the separate thing. I have unions of heads. Okay, so now I want to show you that this is not true only for one specific safe matching, but this is true for the entire set of safe matchings, okay? So what do I know about the set of safe matching? I have the worst matching here, the empty matching, and I have the top matching there, the men optimal. It's stopping for the men at least, right? Men optimal safe matching. I also know that if I have 2 safe matchings, then I can also do the join, meaning that there is some semi-lattice here, okay, that is connected by the preferences of the men, okay? I can also show that if I look at just the set of safe matchings that have all the same support, then this set of safe matching is actually a sublattice of the set of stable matches on those agents, okay? Which makes sense. Nobody blocks, right, within this set. So I can kind of separate this graph into different supports. Each support is now a rectangle, okay? And I can sort of draw a graph here that says this is the worst one in terms of supports, and this is slightly bigger, right? And those 2 have 2 other sets of agents to join, and so on. Turns out that this is impossible, okay? This specific drawing. Why is it impossible? Because I can show that multiplicity never collapses. If there is multiplicity of safe matchings here, then this multiplicity would persist upward, and same here. So it really should look something like that, okay? If I have 4 possible safe matchings for those new agents that I added on the left side, and 2 safe matchings for the agents I added on the right side, then I have 8 possible options here, okay?
What is the upward arrow?
Say again?
What does an upward arrow mean?
Oh, preferred by all men. Preferred by all men. Weakly preferred by. And this is just because I didn't want to do all the errors, right? And then what I can also think, another way to think about that is just to think about the set of agents that are being matched in each of those, okay? And each of those sets is kind of like a tier, a new tier in my graph, okay? So I have the top tier, S1, and I can only match S2 in a safe matching if I have S1 before that, okay? If I also match S1. And I can only match S4 if I have S3, okay? And I can only match all of, so I build kind of a directed acyclic graph of tiers, okay? Each tier pointing to tiers above it. But I can have 2 second tiers, right? So this is a second tier and this is a second tier. And within those tiers, I have different options for how do I match those agents. And what I get here is just the cross product of those matches. Good. So I can look at those tiers like that, and I got a generalized hierarchical and separate structure of the set of safe matchings. So now it's not just one safe matching which is union of heads, it's the entire set of safe matchings which looks like a tier structure, okay? And I can also calculate, I can also find those tiers using the algorithm that I did before, the IBDA algorithm. How do I do it? I first run in IBDA for all the market, and then I each time try to remove one agent and run the algorithm again, and I see what agent do I lose. the minimal sets that I lose are the bottom tiers, right? And then I can remove them, and then find the other tier, and the other tier, and the other tier, okay? And that's how I can get all this graph in, well, not the matches, but the sets I can get in O of n to the power 5. Okay, incentives. It's well known that men proposing deferred acceptance is strategy proof for the men, okay? I mean, truthfully. For IFDA, that depends on how you interpret the results, because thinking about the result of not being matched as the worst thing that could happen to someone it just doesn't make sense in this story, right? I mean, if this is a recommendation system and there is an option value of being matched with some firm, then yes, I want a recommendation and not, and I always prefer to not getting a recommendation, and then it's not strategy proof because they can always just remove agents who are going to be burned in the algorithm and not put them on my list, and then I wouldn't be burned, okay? But in fact, if the matching has some traction, if I'm actually going to implement this matching, then not being matched kind of indicates that I'm going to be matched outside of those people who are matched. Maybe to agents outside of the market, maybe it's Chandler and Monica that are likely to be matched if Richard doesn't like Monica, okay? So you could also think about IBDA about the results as what happens if, for example, Chandler is optimistic. He believes that if he's not matched, then he will get his top choice out of those people who were not matched, okay? Then it's also not strategy proof, by the way, okay? Because then someone can intentionally create a burning chain that would burn someone that he likes, but that's technical. And then there are other interpretations. I still haven't found an interpretation that would make it strategy proof, and I kind of think that it's not likely that I will find an interpretation that makes it complete strategy proof, but different interpretations would give different incentive properties. So the second interpretation I mentioned would make it, let's say, more likely for someone to not lie, okay? Okay, many to one more. The whole thing, I kind of started with firms and interns. Firms obviously hire more than one intern, most of them, and I talked about one-to-one matchings. It's easy to move to many-to-one matching, okay? How do we do it? Instead of burning firms, I just burn positions in firms, okay? So if a firm wants a student from Tel Aviv, okay, and this student does not participate in our matching, I only burn the bottom position of that firm, okay? If they would want another student, I would burn 2 positions and so on. It's pretty easy. It wasn't easy for me when I did the actual matching, which is why I did the firm proposing version, not the student proposing version, because it wasn't clear to me in my mind how to do it in a student proposing way. Now it is, and in retrospect, I wouldn't have done it like that, but that just shows why we need such theory, okay? Before I do the summary, I have like 2 minutes, right? Let me say that if you do that for the low intention, so what? 4 minutes, good. 2 minutes I'll use to say something about what would have happened if I actually used the IBDA algorithm for the low internship match. In the low internship market, it is traditional that the Supreme Court actually doesn't hire anyone by the time the market clears. So they wait for the market to clear and then they just pick whoever they want, and those people break their contract with the firms and come to work as Supreme Court clerks. We couldn't possibly convince Supreme Court judges to participate in our matching system, okay? We knew that. Now, Supreme Court judges are like the top position, right? So supposedly I should have burned my entire market on the first step and that's it. Everybody wants to work at the Supreme Court, so I could just burn everyone and that's it. But that would not be practical, right? That would I mean, I'm trying to improve the market that currently exists. So I decided to just forget about the Supreme Court and do something similar to what happens in the market today, only better. Okay, so we should take this entire thing as kind of a baseline, something that informs us about what we could do and not exactly what we should do. Okay, I think it's not very different from deferred acceptance. Even if even in the years that I did have the entire market, I didn't have the Supreme Court, and still I ran deferred acceptance, right? Okay, one last thing is that for anyone,
So actually you find the matching to be safe, ignoring some agents.
Yes, exactly. Like, which is similar to saying their acceptable agent list is just empty. They're not. Nobody is acceptable to the Supreme Court, right? For now, and just ignore that. There are different ways to look at it, but the specific way that I said just falls nicely in our theory.
Okay, you can make it. You can define it theoretically. You can.
Okay. One other thing I want to say is that if anyone is interested, there are a lot of, let's say, other markets that I could kind of think about in the same way. So I'm right now a master's student doing the same kind of intuitions, same kind of thing about partial matchings for housing markets, for top trading cycles and so on. But you can think about it for practically all markets that we do in market design. Nobody ever does this kind of intuition, and I think it would work for matching with contacts and matching with salaries and assignment games and object allocation. All of that could apply the same kind of framework. So if anyone is interested, I have like at least that long of questions that you could work on, and I would be happy to show you. Good. That's it. Thanks.
If anybody wants to ask a quick question.
Yeah.
If you say that the Supreme Court can hire whoever they want, does it cause the incentives to firms not to take the best candidate?
Yes, but that's also true today. So that's what I'm saying.
They still want to take the best candidate,
Yes, they do.
even though they're likely to lose.
Yeah.
I have a question on scale and convergence. So have you asked the question of what happens when the vast majority and the most influential firms and the top candidates are both participating in the market? Is it possible that they, with implicit participation, the ones that don't participate? That's one thing. And the second thing,
That's a good thing.
yeah,
Okay.
for the
Yeah.
model.
Yeah.
And the second thing is, does it converge at some point to the, assuming you still don't get 100% participation, but it can still at some percentage converge to the stable matching? Or can you say that it's fundamentally different, that even a small number of non-participants can break the traditional stable matching?
Okay, so let me answer both. First question, yes, you're correct. Also, let me just add, giving any recommendation adds more safe. I mean, it's more obvious what would happen in the market, and people tend to follow the recommendations even if they weren't safe, right? Even if the recommendations were completely random, some firms would like it because it's kind of a two-sided recommendation. Both sides know that this is what should happen. So that's one thing. As for what you said, work in progress, okay, and really depends on the market structure. If you have one agent which is in the bottom tier, then yes, you get a stable matching. Okay, if you have one agent which is at the top tier, you're probably going to ruin everything. If it's a random market, well, there are no real uniform random markets. Sorry to blow this dream for some people who are doing uniform random markets, but if it was, probably the agent would ruin everything as well, because random markets are not true. But okay, thank you.
Just got to thank the coordinator and Michal and Noam who's not here at the moment, and they also come, and also Natia Gil from the Center Institute of the Advanced Studying for organized. And next talk is by Niva Elkin-Koren. Sorry, let me introduce her. So Niva is a professor of law at the Faculty of Law. She is the academic director and Chief Justice of Chief Justice Meir Shamgar Center for Digital Law and Innovation, and co-director of the Algorithm Governance Lab at Tau Innovation Lab, and a member of the Academic Management Committee of Tau Center for Artificial Intelligence and Data Science. And she's going to talk about harnessing general agent and AI to inform legal decisions.
Thank you so much. This is great to be here, and as you could have learned from the introduction, I'm not an economist and I'm not a computer scientist, but I've been working in this intersection of computer science and law, so we're going to stick to law. We've heard about legal internship, and now from a completely different perspective. And here in this intersection of law and computer science, this is a community that is still a work in progress. Some of the faces I see in the audience are, part of this. I've been working on building this community, but those of us who are working in law were actually looking at computer science as a phenomenon, right? As a disruption. Something is happening. There is technological development, and this disruption requires requires the law to sort of adapt to this. And I think for computer scientists, the law used to be just like an interesting challenge, right? Like matchmaking interns or whatever. I think what we've seen in the past couple of years, and I think that what makes it interesting, and I would like you to think of what I'm going to discuss as a case study for that, is that first of all, we lawyers start to look at computer science as part of the solution to some of these disruptions, and that is where the interdisciplinary work of legal scholars and computer scientists come into place. And what I also figured is that the law as a procedure becomes more useful, I think, now for the development of some of these solutions that are emerging, especially in the context of LLMs. So I'm going to quickly try to describe all of this by looking at copyright law, that is one of the legal regimes that had to adapt to a lot of technological changes, starting more than 300 years ago with the printing press. And it's actually a law that assumes that you need to provide incentives to authors in order to develop their creative works, because it's expensive. It was expensive in this technology because you needed to print, you needed to write, and then you needed to print the first copy. This technology actually made the printing of copies, the distribution, cheaper, and then threatened the incentives for authors that actually worked on writing this manuscript. Therefore, in order to sustain, to preserve these incentives, the law actually creates a bundle of rights, exclusive rights, for creators. So if someone copy without their permission or do some other things that are actually listed in these copyright laws, and they differ around the world, then an author can go to the court and get an injunction, right, or get compensations. Why do we have this very limited list of things that you cannot do without the authorization of the copyright owner? Because we don't want owners or creators to have like a full monopoly over their creation. And that is the purpose of all of this regime, is not simply to reward authors. It's actually to create works, to ensure that someone invests in writing books, in developing programs, in producing films, and make them available to the public. And so our idea is that we actually, the whole idea of providing these incentives in copyright is in order to actually boost the public domain, to make works available to the public. And also another assumption that is important for a discussion is that in order to promote progress, as we're told by the American Constitution, and that is the actually the foundation of the incentive paradigm in copyright law, we need to have access. None of us can write without access to previous writings. None of us can develop programs without learning how to program, using other programs, using other code. And therefore, in copyright law, we need to sustain some balance between the two. So with this in mind, we now face this disruption of generative models that change the way, first of all, change the way we create, the way we write. All of us experience this, all of us experience this in writing recommendation letters, in writing your papers in school, in programming, but also in producing some videos, films, music, all of this. And that creates several disruptions to the law. Let me just quickly go through the authorship, just because if we'll have time, we can discuss more of it during the Q&A. But the question of authorship is, of course, a huge disruption for copyright law in the era of cheap creativity, where it's really, really cheap and easy and costless sometimes to actually develop new, very attractive works. And so when you look at the law itself, copyright law protects works of authorship. Now, how do you translate this into this machinery process where a machine is being trained on some works of authorships created by others, maybe by other systems, right? Like as we've seen in the DeepSeek dispute now in the United States versus China. But it is being trained on some works and create works that are worthy of prizes and protection or aesthetic as well. This is not the first time that we are facing it. Technology always actually challenged the law, and this is we've seen that with photography, right? And so, like more than 100 years ago, when we had this is a famous photograph taken of Oscar Wilde, and it goes all the way to the Supreme Court, asking whether a photograph that is simply creating a copy of reality by a machine, right, whether this is copyrightable. And these are the same discussions that we hear today, whether sometimes something that you generate with a generative model is just mechanical, it's just a production of a machine, and whether it's a mere copy of something that has been created actually by others, those who actually created the training data for the system. And 100 years ago, it was already, more than 100 years ago, it was already held that photographs could be copyrightable if they original in their selection, disposition, arrangement, in the choice of light and shade, and they're worthy of protection. The fact that they actually replicate what we see in reality is not a reason not to protect them. A second question is, of course, who is the author? And the author in copyright law is the originator of the work. And again, in the world of LLMs and generative models, we have a new question, a big question mark. Who is the originator? Those who created the training data for the foundation model, those who trains the system, those who fine-tune the system on particular data sets, or those who are making the prompt in order to create the film or the program. And we know that this is a very simplistic picture, just because in this value chain you have a lot of stakeholders. Those who create the LoRa's are those participants in this value chain, yes or no? And we have dozens of legal opinions and legal disputes on the way, just to give you a sense of how how we can think of this question. If you think of Little Prince and the pilot sitting, when the pilot, Little Prince asks the pilot, draw me a ship, and the pilot is drawing this ship. This is like us writing a prompt, and then the ship is too old, and it's too skinny, and it's too little, or it's too big, and then big, and then the little princess says, the pilot is painting this box, and the little prince asks, where's the ship? And the pilot says, it's inside the box. And little prince says, that's a good ship. Okay, so this is like recognizing something as sort of the output that you wanted after iteration with your generative model could also make you an author or the originator of that work. But the big question is, who is the author in all of these interactions? This is something that, as you can see, United States Copyright Office is debating on this just from January, from last month, right? Copyright law does protect output of generative models, but it requires some sufficient human control. And the question of what is sufficient human control will provide jobs for all of those people who will be matched with the internship system we heard about before. Now let's move to the disruption that I do want to discuss, that also some of our work relate to, and that relates to liability. So the question of when do we see infringement, when do we, and what do we do about establishing and proving infringement in copyright disputes. And we have here two types of legal disputes related to copyright infringements addressing generative models. One set of disputes relate to the use of the training data as an input for training the model. Again, I will talk about this briefly. And the second type of disputes relates to the question, what happens if you train on a particular data set, and all of a sudden you get an output that is similar to something in the training set, or to something that did not appear in the training set, but looks like Van Gogh or Picasso or anything else that is protected by copyright. As you can see, dozens of, a lot of laws, class actions especially, of authors against, the producers of models, but also some individual lawsuits. The most, I think, famous is probably the New York Times versus OpenAI, but you have also lawsuits against GitHub and a Copilot by Microsoft, etc.
Do they sue? Why do they sue OpenAI and not the use of the text the prompt? So
The what?
why do they sue OpenAI and not the use of the text the prompt to OpenAI?
There are many reasons why, but obviously the first reason that comes to mind is that these are the big pockets. But also because what you want to do actually is you want to have, if you can get a deal here, that those models would actually license the work in order to allow all of us to do the prompts, that would be a much better deal for authors, guild, for producers, for creators in different industries. And so, but these are strategic questions about litigation. And I want to talk a little bit about liability. So here are the tools that we are looking at. And so when do you, how do you determine that there is a copyright infringement? You have to show that someone was exercising one of your exclusive rights. Here, what we are looking at is particularly the right to reproduce, my exclusive right to copy my work if I'm the copyright owner, but also my exclusive right to create derivative work. So if I'm Disney and I invented, I created Mickey Mouse, also my exclusive right to create the derivatives, like the video games, the T-shirts, the toothbrushes, and all these derivatives that are actually based on the original. And when you think about what comes out of these generative models, when you say to Stable Diffusion, draw me a ship, that could be a copy of someone's work, and that could also be a derivative work. So first thing is to show someone was using exercising one of your exclusive rights. The other is that this was done without authorization of you, the copyright owner. And the third thing is that you have to show that there are no exceptions. For instance, there is no fair use. So in the world of painting or writing, we had exceptions for learning. And one of the big questions that we are now asking in law is whether the same exception for learning would apply also to machine learning, to foundation models that are actually being trained. So this is about the input. Just again, as a background, just because this is a new decision of a district court in the United States. It's very recent, but it's also a lower court, but I still want to describe it to you because I think it gives you a sense of at least one context in which these type of disputes can actually play out. And that is Westlaw, that is a data set for using legal opinions that is suing Bros, a startup company that actually developed a generative model that would help lawyers to actually extract the answers to their question. What Rose was doing is actually they hired through another company lawyers that would actually create this type of training data. So lawyers would ask a question. The question would make use of Westlaw, this data set, the database for searching opinions, head notes, and key number system that classify tort law, contract law, copyright law, etc. And these head notes actually refer to part of the legal opinion. Legal opinions are public domain. The questions are public domain. The only thing that could be protected in this case is actually these head notes, these references to some parts of the cases. And the court asks, first of all, whether these are protected, just like head notes that are referring to cases that are public domain, and also whether it was fair use for Rose to actually make use of it if they are protected. And actually the court in this particular context is, to the surprise of everyone, is saying, yes, these head notes are protected. You cannot use it without authorization. And no, this is not fair use. You have to get a license. Is this predictive of what's going to happen in New York Times versus OpenAI? I would say no. And the reason is that these are competitors in the same market, and I think that actually affected partly the result, and the result may change. But this is an important decision that goes contrary to what we've sought in what our Ministry of Justice actually released. Israel was one of the first to release an opinion saying that using the input for training machine learning systems, just using the input is fair use and is not a copyright infringement. And also, I guess most of the scholars actually believe that courts would go in this direction. There is a quick question here.
Could it change in the case of, say, OpenAI, disregarding what they said about the for-profit model they're looking into, but if they're a foundation, a non-profit foundation, does this weaken the argument significantly? They have no competitor.
I doubt it, but of course this is speculation, right? We're only in the beginning. But when you look at Copilot, it's also the same, right? GitHub was It's also something that is different, right? Right, it's also to some extent non-commercial, right? So people put their programs on GitHub, open source. Then Microsoft Copilot is using it in order to train Copilot. And then those developers who put their programs on GitHub are saying, hey, we put it open source, but we didn't mean that you would use it for commercial purposes. And actually that is actually something that arguably, not that it wasn't listed in our license or aren't authorized in our license, but in our license we actually require some attribution, and you haven't given us attribution in the way that in open source communities should. And this goes through the courts. Right now, in preliminary decisions, we see that the court is not accepting this. But again, this is a different context. Let me move forward to the other part, and that is the input. Because one of the interesting parts of the New York Times lawsuit is not only about the input, but it's also about the output. The New York Times is saying, hey, OpenAI, if I prompt your model good enough, I can actually recreate some stories that were published in the New York Times. Now, OpenAI, in this litigation, is answering, well, you can probably prompt the model to generate even things that it hasn't seen. Even if it hasn't seen these stories in the New York Times, if you work hard enough, you can extract something that is very similar or even identical to some of these stories and other stories. And so one of the questions that we were addressing in our own interdisciplinary research is whether everything that you copy, right, is any time that you copy something or that your output looks like a copy of something that exists theoretically in the training set, because we don't know exactly what was in the training set, or in fact was in the training set, would that constitute infringement? And our answer to this legally first is no. And the reason is that there are many reasons why this mob dog looks like this. It's very similar to mobs and to mob dogs. They all look the same, right? And if you had enough mob dogs training the system, it could create a mob dog that accidentally looked like some other mob dog, but not necessarily a copy. In other words, the process of learning is sort of deconstructing these pictures and reconstructing a mob dog. And moreover, in one of the first papers that we published on this, we actually showed that the fact that a photograph exists in the training set and that you can extract a photograph that is very similar to that picture in the data set doesn't mean that this is a copyright infringement. Maybe it is a privacy leak. And privacy and copyright are not the same in this sense. So even if you have an attack on the model which enables you to extract the picture, then it doesn't mean that it's a copyright infringement. And that is because there are plenty of things in this picture that are not protected. Remember, we have to leave enough in the public domain for people to create. We don't protect everything. And so scene of fear we don't protect. We don't protect these standards, you know, the fact that a necklace would be around our neck, or earrings would be here, or the fact that the nose would normally be between the eyes. A lot of things, or the fact that this woman looks like this, which is not protected at all, right? This is part of reality. The photograph with the tiny little choices that the photographer made regarding shade and light, that could be protected in terms of originality. In other words, there are lots of parts of this, of works that are not being protected, and if any similarity between the output and the input would lead to a finding of liability, that would actually stifle creativity and innovation, and would undermine some of the goals in copyright law. All of these things are not being protected, and we actually have to find a way to exclude them from the finding of infringement. These are, for instance, standards we talked about, I mentioned before, the Copilot case, right? If I'm a programmer, I put something on GitHub, and I see in the output that Copilot recreates some program that looks very similar to mine, that might be because we're all using the same standards, and that my original program was sort of a cliche in terms of programming, right? And so we have the same in terms of music and literature and in all other areas. And what we know in copyright law is that the more original the work is, the stronger the protection would be, and the more generic an element is, the less protection it will get. And the question is how to avoid the over-inclusiveness of these generic things that are actually common, and we want everyone to be able to continue and use them. And so here what we were trying to do is to actually to take advantage of the fact that there is some connection between what you see in the training set and what you see in the output. And so it's true that you can have a red car and a blue car and a red bus in the training set, and the output could be a blue bus, but that did not appear in the training set. But there is also a connection between the number of items and the number of colors, and the type of colors that you've seen in the data set, and what you're going to see in the output. And so if we had only pictures with 2 items, we can still see output with 1 item and 3 items, but we're going to see more of the 2 items in the output. And what we have started, what we were trying to do is actually to use this tendency of models to reflect in the output some distribution that they see in the input, in order to get some input for copyright disputes. So we were using something very basic, like in painting. And this methodology enabled us, for instance, to take the Son of Man, it's the man with the apple instead of a face, and to actually, using in painting is to remove the apple, and then to see what we're going to get in the output. And one would expect that the Son of Man is so well known that we are going to see a man with an apple, but we haven't. And what we see, even though we force the model with the clouds, this is exactly the same picture. So this is like forcing the model to actually give you the man with the apple, and we haven't received it. And so that...
Did you ask for a man with an apple?
No, we haven't. No, this is in painting. We actually ask the model to, it's like asking ChatGPT, complete the sentence, complete the missing word. We can do that also for literature. So here what we ask is to actually complete the missing part of the picture.
So what do you conclude from the fact that it did not create the man with the
No, you just get this is the input that the model has to sort of just complete. And that means that actually we cannot actually conclude from it that this is original, but we can conclude from it that it's not generic, because this is a generic, right? And this is, and this type of thing we actually apply to another, that is a real case where you had the Steinberg, this is a very famous
Does it depend on
painting, excuse me?
does it depend on the tool? Maybe for OpenAI it's not generic, but for DeepSeek it is generic.
Yeah, this is a great example. This is a great question. I'll come back to it in a second. And so this is another interesting case, and that the Steinberg picture on the cover of the New Yorker, the view of the world from the 9th Avenue, New York, the center of the world, long time ago. And this in a legal dispute was used actually as a commercial for Moscow on the Hudson. And the defendants were saying, we didn't copy this painting. This is actually a picture of New York City. And, you know, these are buildings and lamp posts and the water towers. This is what you see in every city, especially in New York. That is what New York looks like. And the court actually was looking at the shade as partly the anomaly, right? As something that actually doesn't fit the way the light is actually playing in this picture. But we replicated this, again, using in painting, and so we covered this, we asked the model to complete it, as you can see it, completed it with buildings. And we've done it, you know, a lot, you know, several times. Whereas the infringers here, the defendants here actually copied something that is not generic, but unique or original, yeah.
So the prompt was complete the missing part,
Yeah.
something like that. But if you say, if the prompt was more specific, because it probably did so in the training of it, the real picture. So if you would say completed it like the Hudson, the Moscow on the Hudson or something like that.
Yeah, we could have done that, but
Yeah.
this is not what we were looking for, right? I mean, but you're right, and this is also connected. You're right that this type of testing
Yeah.
depends on the way you prompt the model. This type of testing depends on which model you're using. And actually, you can use a couple of models, and if you see the same trend that is stronger than, oh, it's just on stable diffusion, right? All right. And so, you know, for this, we were actually looking for memorization, right? Would be infringing only if it goes against the natural bias of the data, right? And so we're studying the bias in the data in order to exclude generic ideas in the way that I described to you now. And to say these are generic and they should not be given protection. Right now, judges are actually just saying, I think it's generic, right? But they don't have any way of sort of establishing this. In another set of studies, we actually try to quantify originality, also looking at the way in which the number of tokens that are being used in order to generate a picture could tell us something about the level of originality. But what I'd like to do now is actually to show how this method that we were describing could actually be used in other legal contexts. And so when you think about it, we are actually using generative models as a way to sort of study culture. We sort of assume that this is, if something was learned by the model, that means that this has become common in our culture. And that is an input for copyright, but this is something that is evolving in social science in general. We see more studies that assume computational social science, sort of assume that models embed some knowledge about the world, about the language, for instance. And so when we look, most of the studies actually now in social science focus on the long tail, right? Studies on fairness are saying, well, you cannot, this is so rare, you look only at the head, right? You get a translation that is biased because it looks at the head. You look, you get an output, a diagnosis in medicine that is biased because it looks at what most people suffer from. You don't look at the long tail. But in law, the head could actually tell us a lot of things. There are plenty of contexts in which we care about what is common. We care about the majoritarian rule, like generic trademarks. If Jeep become a name for a particular car, not a particular brand, but a type of car, it is no longer protected in trademark law. And if courts could actually simply check that using generative models, they don't need to have surveys. That is the way that we actually do it now. You can look for input about what the reasonable person would do. In patent law, we have majoritarian rule, what a person of ordinary skills in the arts would know as a benchmark for studying innovation. And what is really interesting is how you could use this in order to interpret contracts. In contracts, sometimes you want to look at what's the common ordinary language, right? Like people will say, you need to pay within a reasonable time. What do they mean? Here in this case, this is actually a way in which a court in this decision, also very recent, was actually using LLM in order to establish a common meaning in an insurance policy for whether something actually falls within or not within that policy. And now the judge is actually a bit embarrassed for using this. And he said, I needed to actually interpret that contract to see whether the insurance policy applies. And I look at dictionaries, and I'm not satisfied by the answer that I get from these dictionaries. And then I looked at ChatGPT, and that troubles me because I know that it has some advantages. It is trained on ordinary language. I can conclude that it may reflect some things that language reflects. By the way, not everything is being reflected by language. But I'm also concerned that LLMs hallucinate. We know that it is vulnerable to manipulation, especially in a legal setting where we have the adversaries of defendant and plaintiff. And we are also concerned that, the judge is reflecting on this. He says, I'm aware that if I can use ChatGPT, the next step would be that ChatGPT would also make the decision, right? I mean, why just for interpretation? Maybe also for the decision. And here I think that there are some legal features that could actually help, and I know that I'm running out of time, but just to say that in law, the legal setting is actually a great place to check that. And the reason is that we have an adversarial setting. So those who will bring the evidence for what the ChatGPT was saying about common interpretation of a term, you'll have an adversary that would bring some evidence from other LLMs or from other tools, or would ask what is the right prompt, and then we may have to standardize the type of prompts. but that could actually, evidence law and legal procedure could actually provide a setting for checking the validity of some of these studies. Of course, you can do that in social science and in computer science using the methodologies that are accepted in these areas, but I think here legal procedure also offers some great tools. So we came along this circle just to say that what the type of work that is needed for using tools like this, and we see now a lot of tools of that sort that are being developed, requires very intimate collaboration of lawyers and computer scientists for taking advantage of the tools, but also of the opportunities created in each research setting. Thank you.
So this was really, really interesting. My question is, I mean, with the current state of affairs where everything is so dynamic and evolving every week, I mean, what was the case last week no longer holds. Can you imagine like a prompt that would be acceptable in the court of law, or a procedure that would be acceptable in the court of law in such a dynamic reality?
Yeah, absolutely. I think that, first of all, the law could develop top-down or bottom-up. Top-down means that, can I imagine a legislator in Israel or elsewhere creating a rule that would actually be sufficiently up-to-date, dynamic, and reflect state of the art? No. Not the regulator and not the legislator. And so the alternative is actually to enable litigants to bring this to court and allow the court to actually come up with some standards. This is how the common law actually developed. This is sort of, you see a bad standard. I mean, I think you see a bad decision, and then an appellate court, decides differently. And then when you have sufficient number of precedents and disputes, you reach some agreement of what the standards that are acceptable. I think that the risk of lobbying, here also, there are also some biases, right? There are big players that are playing in litigation. The big companies have better lawyers. It's not necessarily going to be the best, but I think that you have pretty big players at both sides, and so I'm very optimistic on how these disputes would actually bring about some standards, that would be acceptable in courts.
Thank you for the talk. I have a related question. As I understand it, the process between regulators and courts, and also maybe private companies, is a bit different in the sense that once courts set a precedent, then you have to somehow follow this precedent, and you cannot change it, especially if it's the Supreme Court. So my question is, are the courts aware of the theoretical efforts and are willing to give them some time? Because it takes time to develop a theory of different ways you can compensate the contributors, and so you could come up with different theories, and if the courts already set the precedents, you will be kind of stuck with whatever they decided.
So in the common law system, courts have a lot of leeway. They can say, yeah, we had that rule, but this situation is different. Like I've showed you, it's like we talked about the Westlaw, the Reuters case with Rose, right? The litigation on the legal data set. And I said, this is different from New York Times. This is also the way in which courts could do that, right? Could set a bad precedent and then fix it with other cases that would not fit that rule. And so there's a lot of flexibility, actually, in the legal system, especially using the discretion of courts. And I think that the problem is that not that many judges are so reflective and honest about what they, I mean, this judge actually was writing 25 pages just about this process in order to encourage his fellow judges to use ChatGPT not as the conclusive evidence of anything, but just as an indication. And I think once this process will evolve, we will see more of it. By the way, our Supreme Court, this is not related, just last week held that it was in a case that where an attorney actually submitted briefs with made-up precedents, and so the court did not, Supreme Court did not fine her, but held that this could be a criminal offense, a disciplinary offense, and of course create liability towards her clients, and that lawyers beware.
לא, כדי שזה יהיה מסודר. זה לא כמה. אז בוא נעבור לבא. אני אכן את זה.
לגמרי.
Okay, let's start with Omar Maton from Session1. We'll have a break afterwards.
So, hi, I'm Omer, and I'll talk about the joint work with Idan, Itamar, and Moshe from the Technion. And this is going to be on the convergence of no-regret dynamics in search and recommendation platform. So, it is well known that in these platforms, publishers often act strategically, and their primary goal is to maximize the exposure they gain from the system that depends on their content, but also on their competitors' content. And these kind of dynamics often creates fluctuations in the content that is created in the long term, and this affects the welfare of the end users and also poses some significant challenges for the platform itself. So basically, this can be seen as an unstable state of the corpus within the platform. So the question that we're going to ask is, how can this platform guarantee that publishers naturally will converge to a stable state, to a Nash equilibrium, in which the these fluctuations are being reduced. So we're going to adopt a game theoretic framework in which we have end publishers, and they're going to create documents in a repeated dynamic setup. These documents are represented in some embedding space, and in this embedding space we also have representations for the user's preferences that are drawn from this commonly known distribution. And we consider games in which the exposure for the publishers is determined in a very specific way. It is proportional to G, which is the activation function, if you think of this recommendation platform as a neural network. So it's G evaluated at the relevance of the document to the user's preferences. And the platform obviously controls the selection of this activation function. And the utilities in this game are the expected exposure, where the expectation is over the user's preferences, minus some integrity cost that represents the extent to which the publishers deviate from their ideal content, this content that they would create if there was no competition in the market. And as very common in machine learning and online learning, we're going to assume that the goal of the publishers is to achieve low regret. They want to minimize this external regret, which is the difference between what they could have done if they have known what their competitors are going to do and what they achieve in practice. And in particular, we're going to consider dynamics in which the regret grows sublinearly. So the main result is a connection between the concavity of the activation function and the concavity of the game in a game theoretical sense. So it turns out that in our class of games, the followings are equivalent. So G, the activation function, is concave. All the induced games by the proportional ranking function are concave as in the standard definition of concavity. But it's also equivalent to the social concavity of these games, which generally speaking is a much stronger property than concavity, but it turns out that these are equivalent. And the corollary regarding no-regret dynamics in our model is that whenever the activation function chosen by the platform is concave, the convergence of no-regret dynamics is guaranteed. So this follows immediately from the result by Evan et al. And we also have some experiments demonstrating several trade-offs between the publisher, user welfare, and the stability, which is the rate of convergence to the equilibrium. And that's it.
We'll take questions offline, I guess. Such a
Hi everyone. We talk about approximation mechanism under a budget constraint, focusing on revenue maximization. I'm Rural, and this is a joint talk with Juan Carlos Carvajal from UNSW, and thank you for the invitation. As we all know, bidders often face budget limitations, and this is crucially affects the sales revenue. And for example, Google Ads provides a budget alerts feature to help bidders monitor their spending, and also this is also common in other digital platforms. And what we do, we use the measure of many size complexity. It is suggested by Hart and Nissan. It simply measures the simplicity of an auction using a quantified measure that simply counts the number of different lotteries or options in the auction. And this table shows what we know about various budget constraints. So, for example, without budget constraint, Marson famously showed that an auction with many sizes of one is enough to extract all the revenue using a fixed price mechanism. And if our bidder has a publicly known budget constraint, then the menu size becomes 2. So the optimal auction when the bidder has a publicly known budget is 2, and this is tight. So we need only 2, just to be more precise, we need only, the optimal auction needs only 2, requires only 2 lotteries to extract the optimal revenue. And in the most general case, when the budget constraint of our bidder is private, then Chern-Gale show a distribution for which the menu size becomes infinity. So for this very simple distribution, the optimal auction requires infinitely many lotteries to extract the optimal revenue. So this brings us to our central question. What's the trade-off between the approximation mechanism and the menu size? So more specifically, is there a near optimal mechanism with a small menu size for this case, for a privately known constraint, budget constraint? So I won't go over all. This is just some details of the setting, but the setting is very, very simple. We have a single seller with one item and a single buyer whose type is drawn from some distribution that can be correlated. And maybe the constraint that makes the optimization problem slightly non-trivial or not linear is the incentive compatibility, where we imply the standard incentive compatible constraint. However, we restrict this constraint only to affordable deviation. So this makes the optimization problem perhaps non-linear. And this is our result. So on the negative side, we show that there is a finite distribution for which no approximation mechanism can have a sublinear menu size. So technically, for this specific distribution, any approximation mechanism that guarantees non-trivial fraction, any non-trivial fraction of the optimal revenue cannot have sublinear menu size. So for example, it can't have a square root of the support size. It cannot have a menu size which is with the size of a square root of this parameter. On the positive side, we show that every distribution which is bounded and correlated can have approximation mechanism that can extract 99% of the optimal revenue using a polylogarithmic menu size. And to show this result, we use a revenue monotonicity argument, which shows that even if our buyer has a private value for its budget, then the revenue, if this private value for his budget increases, then also the seller's revenue can increase. This is a slight generalization of observation by Hart and Winnie. Thank you.
Next talk is by Naaman from Emoad from the university.
Yeah, well, hello. This is a joint work I did last year with Mahira Bayo on truthful mechanisms without Pareto efficiency, characterizations, and fairness. Okay, so our setting is as follows. We want to fairly partition indivisible goods among equally entitled agents without monetary transfers. Let's break that apart. So we have indivisible goods. In this example, muffin, cherry, basketball, and croissant muffin. We have our agents. We want to fairly partition these indivisible goods among the agents. Indivisible means that each item is given to one agent whole. The agents are equally entitled, so there are no asymmetries between them, and there are no monetary transfers. So this isn't bidding. We just allocate items, for example, like this. Now, many proposed algorithms for allocating these indivisible items fairly are actually manipulable. What does manipulable mean? Agents are incentivized to act strategically. Depending on the other agents' valuations, they don't have a dominant strategy. So let's give an example. The round-robin allocation protocol. In this protocol, we have, for example, the blue and the red agent. Their values for the items are given here. And each one in turn just picks one good, however they want. Now this protocol is manipulable. If you look at the blue agent, it's actually non-trivial what the blue agent should pick. On the one hand, if she plays greedily, she'll take the muffin, so it's worth 10. But if the blue agent is aware of the red agent's preferences, she can plan ahead and, for example, take the glove, resulting in this chain of occurrences, which ends with her getting the muffin anyway, but also the boxing glove getting more value in total. So we want to design mechanisms that are not manipulable. Let's look at a different kind of mechanism. These are serial quota mechanisms. Now we also have quotas. Quotas are just whole numbers given to each agent. And still in ordering of the agents, at each round I, the agent BI chooses her QI preferred items from those remaining and leaves. There is no cycling, unlike round robin. So let's see an example. In this example, these are the preferences, 2 agents. Blue agent has a quota of 2. She'll take the bell and the apple, leaving for the red agent the book. Now, we're going to consider direct revelation mechanisms. So we want the agents to report their preferences to us, and we'll run the mechanism ourselves and output the resulting allocation. We want a mechanism which is truthful, kind of like a DSIC, which means that if no agent can ever strictly improve her allocation by lying and misreporting their preference. So if we think about the round-robin protocol, if we had wanted to implement it in a greedy fashion, give us your preferences, we'll select the best available item at each round, that wouldn't be truthful. Because an agent would lie in order to alter the ordering in which items are selected. Now, serial quota mechanisms are truthful. We can see this pretty easily because after selecting her items, the agent just leaves. So at that given point, her dominant strategy is to just take whatever items are best. The problem is serial quota mechanisms are unfair. They only give 1 over m of the MMS, which means no constant approximation, and EF1, MMS and EF1 are fairness requirements. For those who don't know, we can talk about it later. But EF1 is satisfied only when most of the items are thrown away, which means the mechanism is either not fair or very, very wasteful. So the question is, are there any mechanisms which are both truthful and fair? Another restriction we'll make is we'll only consider mechanisms which also satisfy these properties of non-bossiness and truth and neutrality. These are 2 common properties. Many common mechanisms satisfy them, and they make the analysis easier. So this is the characterization that we proved. An allocation mechanism over strict additive valuations is truthful and non-Bossian neutral, are 2 additional assumptions. If and only if it is a serial quota mechanism, and the corollary we get is that it's unfair. I mean, no constant fraction of the MMS, and we don't get EF1 unless we throw away most items. Now, we can actually generalize this much more. It holds even when the mechanism doesn't need to allocate all the items. So what we talked about EF1, we can try to throw away some of the items to get fairness, but then we'll get a very wasteful mechanism, and the characterization still holds. And we don't even need to restrict ourselves to added evaluations. In fact, this holds for any class of strict and monotone preferences. So it holds both for cardinal valuations, which give values, and for preferences, which just in ordering over subsets. And it holds for any such class, as long as it contains the class of lexicographic preferences, which is a small and restricted class, which is within the additive. So, just to give you some idea, additive evaluations, sub-additive evaluations, the class of all monotone preferences, all pretty much most common preference classes, this theorem also holds for them as well. Thank you, and if you want questions, I have to
Hello, I'm Ariel from Ariel, but I'm presenting in behalf of Eden Hartman, who is a PhD student who cannot come because she's now in AAA. So this work started when we wanted to implement mechanisms for real-life problems like fair course allocation in our university or fair budget allocation for our student association. Initially, we wanted mechanisms that are truthful, that cannot be strategically manipulated, as Noam just explained. But we found out that truthfulness is often incompatible with other desired properties like fairness, efficiency, and budget balance. Thanks, Noam, for giving a great example for this. So we relaxed our truthfulness notion a bit. We are looking for real mechanisms, so we want mechanisms that are less likely to be strategically manipulated. But this work is still theoretic, so we do need some theoretic assumptions on the agents to define what we mean by less likely. So we assume that risky manipulations are less likely. If there is a manipulation that can bring you gain but can also be harmful to you, you're less likely to take it than a safe manipulation where you can gain but you can never lose. Second assumption is that collecting information on other agents, on what they're going to do, what they prefer, is hard. It's harder, for example, than computational hardness. Computation now is quite cheap and easy, but collecting information on others, you need to interrogate them, you need to spy over them. Okay, so based on these two assumptions, our solution concept is to design mechanisms that require a lot of information to have safe manipulation. That's the concept. We have a formal definition in the poster. You are welcome to come. Informally, we define for each mechanism in every social choice problem a degree, which we call the risk avoiding truthful degree, RAT degree. This is defined as the smallest number of agents whose reports, if known, allow another agent to safely manipulate the mechanism. By safely, I mean that the agent can gain for some reports by the unknown agents and can never lose for any reports of the known agent. It's a worst case because we want to be we did not want to make assumptions on distribution, so we went on a worst case definition. Okay, so this is the degree. So the lowest value for the RAT degree is 0. It means that there is a safe manipulation, a manipulation that you can never lose from it. So even without any knowledge, so a rational agent will necessarily want to manipulate. This is the worst case for the designer. On the other hand, a truthful mechanism has the highest RAT degree of n, because even if you know the preferences and the actions of all other agents, you still cannot manipulate. In between 0 and n, you can grade all existing mechanisms on a scale between 0 and n that tells you how hard it is to safely manipulate in terms of informational hardness, how much information you need in order to manipulate safely. Higher is better for the mechanism design. That means it is harder to safely manipulate. Then we started to look at various social choice domains and look at the existing algorithms also look for new ones and see what we can do. So for example, we started with auctions for a single good. We found that the first price auction with discount has an narrative degree of 1, which is very low. Even you can know even one agent and already have a second manipulation. On the other hand, second price auction is known to be truthful, so its degree is n, which is the best. But its revenue it might be low if you have risk-averse buyers. With risk-averse buyers, you don't have this revenue equivalence, so the revenue might be low. But if you take the average between the first and second price, interestingly, the narrative degree is n minus 1, which means that you might have a higher revenue, but still with a mechanism that is very hard to manipulate in terms of information. This is one nice example that our theoretical definition also guides us to new mechanisms that can be useful. I did not find any mention of this mechanism. Maybe it can be attempted and maybe it can be useful in practice. We also studied the single binary voting. I will not give it. The details can be seen in the poster. We have some preliminary results on stable matchings, on fair cake cutting, on indivisible goods allocation, and we keep looking for new domains where this concept can be used. So if you have any domain in which truthful mechanisms are too restrictive, we'll be very happy to discuss whether our concept can be helpful to you. Thank you.
Thank you, Ariel, for noticing I forgot my glasses today. גם אז אני לא רואה את זה גם, אז אולי נמשיך כן, אז אולי נמשיך בתיה הבאה. אז שאול, תמשיך לך כאן.
So I'm Shaul, I'm a postdoc at Tel Aviv, and I'm going to give a short model and example, and that's it. That will take me 5 minutes. So this is a work in progress with Mark Schroeder and Laura Vargas-Koch from Maastricht and Aachen. Okay, so what's the model? We have a directed graph, we have a source S and a sink T. We all know max flow min cut, so this is dynamic flow. We have a rate of flow of units of flow are entering the network in every second, and every edge has a capacity. We're used to that, but it also has a transit time, how long it takes for the flow to pass the edge, and it also has a toll C. This is how much it costs to use the edge. This is a well-known model. The modification that we're making is the addition of the toll, not only transit time, the toll as well. Okay, so what happens? Flow enters the network at the rate of u, and excess flow results in a queue forming. So if we have a capacity of 1 on an edge and we have incoming flow of 2, then a queue is going to form at a rate of 1, which is going to increase the transit time on the edge. And of course, if we have less flow going into the edge, then the queue will decrease and we'll never have a negative queue. If there aren't enough cars, then the road is going to be empty. So a transit time over an edge is the tau e, the transit time of the edge, plus however much q there is when we enter the edge. And the cost of using an edge is the transit time plus the q plus the toll for using the edge. And what is going on is particles of flow attempt to reach t through a cheapest path, cheap meaning cost plus travel time. And this gives us this nice equation that you're welcome to check, but basically the particles will choose the edge, which will result in them having a minimum cost. Let's see an example. We have a very simple network, S to V T, and we have a choice. First of all, between S and V, we have sufficient capacity, and our choice is between a toll of 1.5 for 0 transit time, or a transit time of 1, but no toll. for between V and T, we again have a choice. We can either just go to T immediately, or we can do it over a path that takes 100. So the second choice is simple. We're definitely going to take the bottom. We're going to take the top edge. However, Q is going to form because we only have a capacity of 1 and an incoming flow of 2. So the simple solution would be, let's take the bottom edge into the top edge until the Q becomes of length 100. And then we'll just split the flow between the top edge and the bottom edge between V and T, and everything is nice. And there's one problem, that this does not work. Why is this a problem? So first of all, the Q between V and T is growing at a rate of 1, which means that if we arrive at V 1 second faster, we're actually saving the 1 second of the Q increasing. So actually the top edge is better. But there's also another problem, that at the moment when we, so we do need to use the top edge at some point, and this is still a problem. Why is this still a problem? Because at the moment when we switch from the top edge to the bottom edge between S and V, switch from edge A to edge B, the Q between V and T is going to decrease. There will be 1 second where no flow is arriving at V, which means that the Q between V and T is decreasing, which means it's once again better to take the top edge. So the question is, what is the equilibrium here? What's going to happen? Okay, so this is actually what I said. The final flow distribution is clearly correct. At some point, we're going to split the flow evenly between the edge C and the edge D. But the question is, how do we arrive at that point? So what actually happens? As I said, the flow has to start at edge A. It's going to pay a total of 1.5 to arrive at V immediately, meaning that the Q on C is starting to grow immediately, meaning that all particles until time, and as long as this is the flow, will have a cost of 1.5 plus theta. 1.5 for the edge on the edge A, and theta for the Q on that is slowly forming on the edge C. Now, why time 98? This seems kind of arbitrary, and this is because we need a transition phase. And this is what's going to happen between 98 and 99. Now, half a unit of flow is not going to use the edge A, it's going to use the edge B. Why half a unit of flow? Simple, because now that the Q on the edge C is only increasing at a rate of 1/2. Okay, so what happens at time 99? Once again, another half unit of flow is going to shift from the edge A to the edge B. But we still have the Q on C increasing by 1/2. Why? We have 1 unit of flow arriving immediately through the edge A, and we also have half a unit of flow that is coming from the flow that went between 98 and 99. We go to the time between 100 and 101, another half unit of flow, and this is now the Q is once again growing at a rate of 1/2. Why? We have 1 unit of belated flow from the time 99, and we have half a unit from the current time. And at time 102, the Q is still growing. Now all of the flow is going through the edge B and not the edge A, but we still have 1.5 units of flow from the previous phase, and only finally at time 102, the Q on the edge C arrives at 100 at exactly the point where we have no belated flow, no extra belated flow. All of the flow is going from the bottom edge, or the rate of increase remains 1, and this is the only dynamic equilibrium for this specific instance. And that's all I have to say about that. If you want to see some more examples and actually hear results about this model, I'm with the overly large poster.
Thank you.
So my name is Matan. This is joint work with Martin Bollinger, and it's part of my MSc thesis supervised by Edith Elkind. Okay, so I'll talk about complexity of popularity in hedonic games. I'll briefly explain several models that we study here of hedonic games and what they are actually. We'll talk about a specific stability notion that we're interested in, and some complexity results. If we have time, some future work that can be done here. Okay, so what are hedonic games? It's quite simple. We get a set of agents, and we want to partition them into coalitions. Okay, and obviously these agents are going to have some preference order over all the possible coalitions that they can be part of. And hopefully we can find a way to partition them in a way that reflects those preferences. So you can think of some examples like division of players into sports teams, or PhD students being allocated into research groups, political parties, coalitions of political parties, and customs unions agreements between countries, and many, many more. Okay, so in the most general case, we have a problem of representation because one cannot really specify preference order over all the possible coalitions because there are exponentially many such coalitions. So we need some compact representation of these games. And what we do is we consider two, at least in this project, we consider two very common models. The first being additively separable hedonic games. So those are just additive games where each agent has a single value associated with any other agent. So for instance, here the owl has value of 2 associated with the sheep, and value of 1 with whatever that is, maybe a penguin. And then the utility of an agent given a specific partition will simply be the sum of the values that they assign to agents within their own coalition. So in blue, I highlighted the utilities of each agent in this specific partition. Okay, so the owl gets a utility of 2, which is just the sum of this number over here. So this is obviously easy to represent. We just need a polynomial number of values. And the second model is very, very similar, except instead of the sum, we take the average when we consider a value of 0 to ourselves, but it doesn't really matter. So here, the owl would get a utility of 2 because this is the sum divided by the size of the coalition. So divided by 2, and we get a value of 1 for the owl, and we stay with 0 for the other 2 agents. Okay, what is the stability notion that we're looking for? So we want to seek partitions that are kind of stable, but we don't expect to fall apart into any other partition. And we're going to look at none of these. So these are kind of the maybe an example of some of the more studied ones. And we will look at something called popularity. So what is popularity? A partition pi star is called popular if whenever we compare it with any other partition, a majority of the agents will prefer the popular one. Okay, so take a look at this pi star. If we compare it with pi, for instance, the owl and the sheep both prefer pi star. You can see the utilities here. So this is the blue is just the additive values, just specifically, not the fractional one. So we have 2 agents preferring pi star, and if this holds for any pi that tries to challenge pi star, then pi star would be called popular. Okay. So let's jump ahead to the results. It was previously known already that it is, okay, sorry, let me back up a little bit. Existence is not guaranteed here, okay? There doesn't always exist a popular partition because it's not a transitive property, okay? So it can be the case that we have cycles and none of the partitions are actually popular. So we are interested in this existence question. Given a set of agents and their preferences, can we determine if there exists such a partition? So it was already known to be NP-hard and co-NP-hard in both of the models that I introduced to you. And in this work, we actually show that it's sigma 2p complete for both of these models. And we can talk about this a little bit more offline if you want. This is just an example of the kind of unfriendly gadgetry that's involved in the reduction. And this is the problem we reduced from, which is kind of the canonical sigma 2p problem. Okay, so just a few words about future work. So there are other models that are worth studying. For instance, strong popularity. So I kind of neglected a few details, but I was talking about weak popularity, which means we need only a weak majority over any other partition. If you consider strong popularity, which needs a strict majority, you can only have at most 1 such partition because 2 cannot beat each other. 1 has to beat the other. So this brings a lot of interesting complexity questions about unique solutions and stuff like that. If anyone's interested, we can talk about it later. Mixed popularity, another model that's quite interesting about distributions over partitions. I won't get into that. And one can consider symmetric graphs. So what if the agents all have symmetric preferences towards each other, which we also conjecture that it's also going to be significantly complete, whereas here it's probably not, actually. Yeah, that's it. Thank you very much.
Yeah, Alon was my supervisor. Hello everybody. I hope Asaf spared me some of the preliminaries because I'm also dealing with a two-sided market. We have doctors and hospitals. Each doctor is looking for an hospital. We don't have the okay, never mind. Each doctor have a complete preference list of which is random in our case of hospitals. He wish to get the best hospital he can, and vice versa, hospitals also. And default acceptance algorithm, which is pretty old and everybody use it, everybody keep investigating it by more than 60 years now. It goes as follows. Doctors are active, they just approach and propose to their most favorable hospitals. Hospitals are passive, but when they receive proposals from several doctors, they keep their most favorable doctor and reject the others. And it guarantees a stable matching. So it was shown during the 80s. Okay, the rank is the average rank is a final matching. Actually the sum of proposals doctor made, because they are making proposals according to their preference list. So it was shown during the 80s that there is a big advantage of proposing, that because doctors are active, their average rank will be theta of log n, and hospitals' average rank will be theta of n over log n. That's a big difference that implies that you got to be active. But recently, during the last decade, it was shown that in an unbalanced market of n+1 doctors and n hospitals, the advantage of proposing vanished entirely. The ranks are swapped, and even though the doctors are active, their average rank will be theta of n over log n, and the hospitals will be theta log n. So we asked if this effect might be mitigated under some assumptions, and we are also motivated by the endowment effect, which was shown in some behavioral economic studies, that people value what they have more than what they don't have. So we model it by loyalty. And now, how we model loyalty? We are setting a loyalty parameter of k, and our hospitals, if a doctor approach them and ask them if they will accept its proposal, they will accept it only if they prefer it by more than k positions over the current match. Okay, so in balanced market, that's a general case of the normal DA, this assumption of loyalty. So in balanced market, simulation shows, and also we have proofs that it remains the same. The doctor's average rank is still theta of log n for every loyalty parameter. But in unbalanced market, we know that when k is 0, that's what we said, when there is no loyalty, the average rank of doctors will be theta of n over log n. And when k is n, that's ultimate loyalty. It's like a balanced market, and just adding one extra doctor that will get rejected by all hospitals, and it's equivalent to balanced market, it's theta log n. So we're asking what's in between. And what we found that even when the loyalty parameter k is even less than n, when it is more than n minus square root n, it remains theta of log n. But and also for 0, what we said before, that it's theta of n over log n. But we found that during most of the values of k, between k n over log n to n minus square root n log n, it's about a theta of square root n. And here it's in a simulation. Okay, that's it. What we just to finish it with some words, that we believe, I didn't mention it before, but the DA is widely used. and we wanted to fix it. I mean, to fix the counterintuitive of a transition between going from a balanced market of like a million doctors and million hospitals to million and one doctors and million hospitals. And we believe that even though there is much more work to do, when we are adding loyalty, that's a big important step to start mitigating this effect and making the DA algorithm more realistic, especially in unbalanced markets. Thank you very much.
Last talk is by Tom. So it's here. You see me? Yes.
Hi, thanks everyone. So I don't have a poster. You can catch me later today or at some time. I'm gonna overview some work in progress I have with Mateusz Ferreira and Max Resnick. And it relates to a grander theme of studying auctions, more robust auctions. So generally you usually restrict auctions to be maybe incentive compatible or something like that. But you could more generally restrict auctions to have some guarantees against minor manipulation, auctioneer manipulation in blockchain settings. You would call it minor manipulation or collusion, which is what we study here. Okay, so a few notions of collusions were studied up to us. One of them is like welfare maximizing collusion. So the idea in welfare maximizing collusion is maybe you have some auction format, but ex post you would somehow lose welfare in a way that you don't want to lose welfare in this way. So an example is if you have someone who sets a posted price for you or some second price with reserve, but actually when bidders arrive, none of them can afford the posted price. This is a waste of welfare because you have the spot or the item and you can allocate it to someone, but you will need to somehow lower the price for this event. And maybe the auctioneer and the bidder can somehow compensate each other. So you do need to follow the auction as defined, but there will be some cashback from the auctioneer to the bidder. But the natural question to ask in this case is how can the auctioneer trust the bidder that they say they want a discount or they need a discount, they cannot afford the posted price, but then everyone will ask for this. So how do you deal with this? So the natural way to deal with this is some kind of Bayesian framework where you have a prior over bidders that come, and you need to set up the collusion in advance in a way that will be that the collusion itself will be incentive compatible and everyone will benefit on average. And in the case of posted price, the ways the incentives work is that if the price is really high, above the monopolistic price, then the auctioneer does want to lower the price because they can have higher demand if they lower the price on average. The bidder always wants to lower the price. So this already gives you some structure on if you have an automatic process that decides the prices, if they set the price too low, or they set the price in the low part of the scale, then there would be a contrasting there would be a contrast between the bidder and the auctioneer. The bidder would want a lower price, but the auctioneer would want higher price. But if you would set it too high by this process, then they would could both cooperate to bring the price lower. So it kind of teaches you in which way you might want to make the mistakes with your process. And more generally, you could ask, you could ask how you would collude against a multi-bidder auction.
And then it depends. So there is one case which is the welfare maximizing type of collusion that I described, but there are also other types of collusion where subsets of the bidders might want to collude with the auctioneer. So maybe the auctioneer wants to offer some alternative process to allocate the item, which would give more revenue to the auctioneer. But because of bullet clamper, you might not do it against some of the auctions. So there's a lot to take here. Yeah, that's basically the basic overview of the problem.